Welcome to the deep dive. Today we're plunging into something so fundamental you might not even think about it much. Motion itself.
Right, it's absolutely everywhere.
Exactly. I mean, think about it even as you're listening to us right now. Air is moving in and out of your lungs.
Your blood's flowing.
Yeah, and the earth itself, it's spinning under your feet. It's just this constant, pervasive change. So our mission in this deep dive is really to unpack the basic ideas we use to describe all this movement. Specifically, we're focusing on straight line motion.
And how we talk about it using velocity and acceleration.
Right, those key terms.
And what's really fascinating, I think, is just how universal this whole concept is.
Yeah.
From the, tiny scale up to the absolutely massive.
How do the sources define it, basically?
Well, fundamentally, motion is defined as the change in position of an object with time. Simple as that, really.
Okay, change in position over time.
Yeah. And it's not just about, say, you walking down the street. It describes water flowing over a dam, or cars on a highway.
Or even leaves falling from a tree.
Exactly. Or think bigger, cosmically. The Earth rotates, right, once every 24 hours. And it revolves around the sun.
And the sun isn't still either.
Not at all. The sun itself is moving within the Milky Way galaxy.
And the Milky Way?
Also moving. It's moving within what we call the local group of galaxies.
Yeah.
So, yeah, motion is just woven into the fabric of everything.
That's quite a scope. From our own bodies, like you said, blood flow all the way out to galaxies moving. So if something is that universal, and honestly, it sounds kind of chaotic, how do scientists even start to pin it down, to study it?
That's a great question. The first step is usually simplification.
Makes sense.
So for this deep dive, we're going to narrow our focus quite a bit. We'll stick to objects moving along a straight line.
Okay, just straight paths.
Also known as rectilinear motion. It helps us really get a handle on the core concepts without getting, bogged down by curves and complex paths just yet.
Right, build up from the basics.
Precisely. And there's another key simplification our sources talk about.
Which is
Treating objects in motion as point objects.
point objects. So basically ignoring their size.
Essentially, yes.
Yeah.
It's a really useful approximation. And it's valid when the object size is, well, much smaller than the distance it actually moves.
Ah, okay. So if a car travels miles, its actual length doesn't matter much for describing the overall trip?
Exactly. Think about it. This point object idea lets engineers model everything from, say, a bullet's path to a satellite's orbit.
Without getting lost in the tiny details of the object itself.
Right. You don't need to worry about every little wobble if the scale of the motion is huge. It's a brilliant conceptual tool, honestly. It underpins so much of physics.
Okay, so we've simplified the path straight line. And we've simplified the object. It's a point. Now, how do we actually describe the movement? What's the language we use for this change in position?
Well, that brings us straight to velocity and acceleration. They're kind of the two pillars of kinematics.
Velocity, that's just speed, right?
Not quite. It's related.
Yeah.
But velocity isn't just about how fast you're going. It includes your speed and your direction.
Direction matters.
Immensely. Imagine two cars, both going 60 miles per hour. If one's heading north and the other south, they have different velocities.
Because their directions are different. Got it.
It's what we call a vector quantity. Direction is key. And that's crucial whether you're tracking a runner or, a planet.
Okay, so velocity tells us speed and direction, where it's going and how fast. What about acceleration then? I think most people think step on the gas.
Yeah, that's the common idea, but it's broader than that. Acceleration is actually any change in velocity.
Any change. So speeding up.
That's acceleration, yes. But slowing down, what we often call deceleration, that's also technically acceleration,
Yeah.
just in the opposite direction to the velocity.
Okay.
And even just changing direction, even if your speed stays constant, like a car turning a corner.
That's acceleration too.
Yes, because the direction part of your velocity is changing. Acceleration is the rate at which velocity changes. Speed up, slow down, or turn. It's all acceleration.
Huh. That's a really important distinction.
And understanding those two concepts, velocity and acceleration, lets us map out pretty much any straight line journey. We can predict where something will be and when.
And this whole study, this description of motion, that's kinematics, right?
Exactly.
Yeah.
Kinematics. And the key thing here is that it's about how things move, not why they move.
Right. Describing the motion, not explaining the forces causing it.
Precisely. Kinematics focuses purely on the description position, time, velocity, acceleration, without getting into forces like gravity or friction yet.
So for you, our listeners, why is making that separation so important? Why focus just on the how?
Well, it was actually a huge leap forward in science. It meant we could, for example, predict exactly where a cannonball would land without needing a full theory of gravity first.
You could map the how with precision just by observation and measurement?
Exactly. It made physics a powerful predictive tool much earlier than it might have been otherwise. Focusing on describing motion accurately was the foundation.
A really powerful idea, then, that breaking down these huge, complex things often starts with, well, simplifying and just describing the most basic parts first. So what does this all mean for you, the listener? Well, understanding these fundamental straight-line principles, velocity, acceleration, and even this idea of simplifying things down to point objects is really the first critical step.
It's how we start to grasp the incredibly diverse movements happening all around us, from inside our own bodies right out to distant galaxies.
Absolutely. This deep dive has really just scratched the surface of a universe that's constantly in motion. So here's something to think about. What other really complex things out there might we understand better if we started by just observing their simplest components? What else works like that?